Alright, let's go ahead and start Unit 4, Lesson 3. And I apologize for not being able to be here. I wish I was. If you have any questions, write them down and we'll discuss them in class tomorrow. Just any questions at all, and we'll go over worksheets 3 and 4 tomorrow. So after we get into this lesson, your assignments are worksheets 3 and 4. Make sure those are done. We'll discuss them in class tomorrow. Okay, so the idea here of special theory of relativity is that we're applying this idea to things that are going at extreme speeds, hence special theory. Okay? So there's two assumptions that make the special theory of relativity work. Okay? It's a set of mathematics. Now, we're not going to go deep into the mathematics of this, but I still want to throw these ideas out there. Because if you didn't assume these, then it wouldn't work. And the why we take it as a good theory is that these, the theory itself, the mathematics, can explain so much of our observable universe. That's why it's so revolutionary. The first postulate is this: all the laws of nature are the same in all moving frames of reference, or things moving at a constant velocity. In other words, if there's a bee in a jet flying at a constant speed, the bee inside the jet doesn't have to adjust itself to the speed of that jet. Okay, so it stays at, it just flies like normal. It's like us on the earth. We don't have to adjust ourselves for the speed of the earth around the sun, which is actually really fast. And as long as things are moving at a constant speed, then all the laws of nature are the same. You don't have to adjust for them. So another example of that would be if I toss a ball, if I'm a baseball, while moving in a jet. If I want this thing to land back up in my hand, all I have to do is just toss it straight up and down. I don't have to adjust for the forward motion like this, for the forward motion of the plane, and then catch it as it comes down. Now, from an outsider's perspective, you toss it up like this would seem as a parabolic. But you don't have to actually do it once you're inside the reference frame. You don't have to adjust yourself. Okay? So here's an example based on the first postulate. Okay? Here's an analogy. A boy has a ball. Stand on the back of a truck that is at rest. He throws the ball 60 meters per second toward you, which is really fast. What's the speed of the ball when it hits? So here's the boy. Throws the ball. When it reaches you, it's going 60 meters per second. That's, again, based on our first postulate. Now, no hypothetical boys were hurt in this experiment, so we'll be okay. So now the truck is moving towards us at 10 meters per second, and he throws the ball. Okay, so now the truck's coming this way, zoom, hits us. What's the speed of the ball when it hits our glove? The answer is 70 meters per second. And we answered that based on the first postulate. Now, let's consider the second postulate. Now, instead of being a baseball, right, the baseball is now a photon. It's a single particle of light. Okay? Now, what the second postulate is the speed of the photon is 300 million meters per second, no exceptions. Okay? That's the second postulate. Now, if the truck is moving towards us, let's say at a 1/3 the speed of light, at 100 million meters per second, and the photon is released towards us, what will the speed be when it hits us? The speed of the photon would still be 300 million meters per second. That's the special case to relativity. It doesn't work the same as on our scale of relativity. Okay, and that's, okay? So the photon should be going 400 million meters per second based on the first postulate, but it's not. It's actually moving at 300 million when it hits your glove. So the speed of the light is the same whether we're moving towards, whether the source is moving towards us or we're moving away from the source of the light. It doesn't actually change. Okay. So how could we say something so preposterous? what in the world would ever give us an idea that would be so contradictory? Well, that is actually based on an experiment from Michelson and Morley several years before Einstein. Nobody could quite explain this, but Einstein was the first one able to do so. In 1887, physicists Michelson and Morley performed experiments to determine the speed of light in different directions. So to do this, they shot a beam of light going with the Earth orbit and against the Earth orbit. Let me get my globe to illustrate this. So the Earth, here it is, spinning. Okay? Now, what they reasoned is that light should adjust itself towards relativity. So they shot the beam of light with the rotation, which would make it go a little bit faster, and then they shot it against the rotation, which would make it go a little bit slower. Now the details of the experiment you can look up online and go into it more, but basically they used a rotational system of mirrors. And once they got the mirrors' reflections right, then they could tell the speed and they knew the distance. Alright? So when they did this, they got the exact same number for the speed of light. And again, I can show you more about that if you ask me about it. I'll get you more on that later on. Okay, here's an example. Here's what they did. So they knew the distance, and they used this spinning mirror to decide the cycles with the time. Okay? Okay, so the experiment showed that light is going at the same speed for all observers, regardless of how fast they're moving. Okay, and that is the second postulate. It's the speed of light in empty space will always have the same value, regardless of the motion of the source or the motion of the observer. If you're going at 99% the speed of light and you shoot your beam, you're going to see that photon going away from you at 300 million meters per second. An outside observer would see that light going away from you, 300 million meters per second. Okay, so consider a space station in the Starship Enterprise. Here we go, we got an example here. The Starship is now moving away at half the speed of light. The station flashes a beam of light. Okay? And you will see the light hitting you coming in at 300 million meters per second, and the station itself will see it hitting you at 300. So it doesn't work like our examples they're talking about with the baseball. Okay, so again, special theory of relativity is based on two assumptions which seem to be contradictory. Okay, all laws of nature are the same in moving frame of references, and the speed of light in empty space will always have the same value, regardless of the motion of the source or the motion of the observer. And then when it goes on, we're going to do it tomorrow. Actually, we're going to go into the mathematics of it, and we can describe how time is affected by motion, and then we can also describe, it eventually goes into how mass and energy are actually related as well, which is our famous E equals mc squared. Okay, so again, what I want you to work on for the rest of the class is worksheets number 3, worksheets number 4, and then come with questions, come with your answers for that, and we'll discuss them tomorrow. So have a great afternoon. Sorry I couldn't be with you.